Okay, ji, any questions regarding yesterday's lecture? Okay, so we were doing linear phase filters, and this is some these are some more examples of type 1, type 2, type 3 and type 4 filters. So here h of n is given as 1 between n is between 0 and 4. So this is the plot for h of n. It is 1 for n is between 0 and 4 and 0 otherwise. And as the number of taps are odd, so it means it's a type 1 filter. Why type 1 filter and why not type 3? Mere taba? Why it's type 1 and not type 3?
Sir, क्योंकि ये symmetric है.
Even symmetric hai. Yes, absolutely. Because it is showing even symmetry and it's a case of beta is equal to 0. So that's why it's type 1 filter. And when you will calculate its phase response, that's the situation. And in fact, we did it this example in the first lecture of chapter number 5. So probably week 8 का जो lecture है उसमें हमने किया था. And h of exponential j omega is equal to exponential minus j2 omega sine phi omega by 2 divided by sine omega by 2. Now, what is the phase response? The phase response is minus 2 omega, which is shown here. Exponential j की term के साथ whatever is appearing, that would be your phase response. So minus 2 omega. And that's the magnitude response, sine sinc type function. And as we had seen that there were some restrictions on type 1 and type 1, 2, 3 and 4, and there was no restriction on type 1. You can see from here, because type 1 there was no restriction, so it's okay. The magnitude response is a sinc-like function, and the phase response is this minus 2 omega slope, minus 2 की slope के साथ, and actually it is something like that. But because of keeping it among minus pi and between minus pi and plus pi, so we are having these jumps. Any questions? In fact, if you see, the center of symmetry is 2. The slope is minus 2. And the group delay is constant because your phase response is linear, and that group delay is 2 as well, because group delay is negative of the derivative of your phase response with respect to omega, and your phase response was minus 2 omega. So as a result, your group delay is plus 2. Now let's move forward. Or this is type 2 filter. Why type 2 filter? Because this time we are having h of n is equal to 1 between n is between 0 and 5. So n number of taps जो हैं, number of taps 6 हैं. So even number of taps हैं. And why it is type 2 and why not type 4? Because beta is equal to 0. Beta is equal to 0 means even symmetry. So that's why we have 6 taps, and h of exponential j omega is equal to exponential minus j5 omega by 2 sine 3 omega by sine omega by 2, and you can see that the center of symmetry is this, which is 2.5. So that's appearing in your phase response minus 5 by 2 omega, and this time the slope of this phase response will be minus 5 by 2 minus 2.5, and as a result, when you will be getting your group delay, you will be getting your group delay as 2.5. Hamza Mubashir, beta, any question?
No, sir.
Okay, Abdul Majid?
Yes, sir. No question.
Okay. And now it's a type 3 filter. Why type 3? Because we are having h of n is equal to delta of n. This is delta of n. We are getting some non-zero value, rather it is the sample value equal to 1 at n is equal to 0. And then minus delta of n minus 2. There is nothing on n is equal to 1. And at n is equal to 2, we are getting minus value, minus 1. So this is showing us odd symmetry. Number of taps are odd as well. N is equal to 3, 1, 2, and 3. And m is equal to 2. And this time beta is equal to pi by 2. So you can see from your samples that whether beta is equal to 0 or beta is equal to pi before plotting your phase response. So this time, as we had said, there is one more thing regarding this, that you can see that even number of taps type 2 ke liye, there was a restriction that h of pi is equal to 0. Look at this. H of pi is equal to 0. So you can see here h of pi for type 2 filters, h of pi is equal to 0. So whenever you will be having even number of taps with even symmetry, you will be having h of pi is equal to 0. So that was the reason that you cannot make high pass filters using type 2 filters. And now again we are coming to type 3 filters. We have talked about this. So this time the frequency response is j 2 sine omega exponential j omega. Now what is the phase response? The phase response is coming from here. J is pi by 2 minus omega. So this time this j is in fact beta is equal to pi by 2. That is coming from here. ये pi by 2 जो है आपका, this time it's not passing through 0, it's passing through pi by 2. So you can see that in type 1 and type 2 it was passing through 0, but here it is passing through pi by 2 radians, and the slope is minus 1. And you know that the restriction on type 3 was h of 0 was equal to 0, h of pi was equal to 0. So you can see from here type 3 h of 0 is equal to 0, h of pi is equal to 0. Whenever you will be having odd symmetry and you have odd number of taps, that's the restriction you will be facing, that your h of 0 will be equal to 0 and h of pi will be equal to 0. You cannot make low pass filter, you cannot make high pass filter, and you cannot make band stop filter using type 3 filters. Similarly in type 4, h of n is equal to delta of n minus delta of n minus 1, only 2 filter taps, and n is equal to 2, which is even. Beta is equal to pi by 2, which is obvious from the taps that it's showing odd symmetry, and as a result h of exponential j omega is equal to j 2 sine omega by 2 exponential minus j omega by 2. The phase response is pi by 2 minus omega by 2. Pi by 2 जो आपका intercept है, omega by 2 is minus 1 over 2 is the slope of the line. As a result, the group delay is 0.5, and you can see that h of 0 is equal to 0, as we had already talked about the restrictions that for type 4 filter h of 0 is equal to 0. जी बेटा, any questions?
सर ये आप ग्राफ को देख के सिमेट्री कैसे, लाइक अभी आपने टाइप 4 में जो भी करवाया ना ग्राफ
जी,
तो आपने इस पे लिखा हुआ इवन
जी,
नंबर ऑफ सैंपल इज इक्वल टू 2 और आपने आके लिखा हुआ इवन।
हाँ,
तो ये
even
चीज
symmetry नहीं, number of taps. I'm saying that number of taps even है, इस 2 के बारे में बात हो रही है.
अच्छा ठीक है सर, ठीक
Symmetry odd है.
ठीक है सर, बस ये कंफ्यूजन थी।
जी बेटा, any other question? जी बोले
सर n जो होता है वो नंबर ऑफ टैप्स को शो कर रहा होता है, और जो m होता है वो किसको शो करता है?
नंबर ऑफ टैप्स जो है ना, चलें इसको यूं लिख देते हैं. Number of taps is equal to n and number of taps is equal to m plus 1. Different books में different notations हैं, that's the only difference.
Yes sir.
ठीक है. So n minus 1 is equal to m is equal to n minus 1. Any other question regarding linear phase filters? Challenge. Now let's talk about the location of zeros in type 1, type 2, type 3 and type 4 filters. And okay, so that how the zeros of FIR linear phase filters are located, and always the poles will be on the unit circle because they are not contributing anything between in the phase and magnitude of linear phase filters. But for that matter, any FIR filters के अंदर जो poles हैं वो unit circle पे हैं. It is the zeros which is playing their role to get the frequency response and phase response in FIR filters. Okay, we know that h of z, just by definition of the z transform, n is equal to 0 to m h of n z minus n. Actually, we have been using the equation h of z is equal to n is equal to 0 to n minus 1 h of n z minus n. But as we were discussing shortly, that n minus 1 is equal to m, so we can use it. So n is equal to 0 to m h of n z minus n. Okay. जो फिल्टर लेंथ जो है वो आपकी m+1 है, 0 से m तक, तो फिल्टर लेंथ आपकी m+1 है. नाउ इन सिमेट्रिक केसेस, बेटा अगर किसी का माइक ऑन है तो प्लीज उसको बंद कर दे. In symmetric cases, what we are having, in fact, these are type 1. Type 2 filters. What is the condition on type 1 and type 2? We can say that h of n is equal to h of n minus 1 minus n, and that's equal to h of 2 alpha minus n, and that's equal to h of m minus n. So all these are same, and as we are using m, so we will be using this thing, h of m is equal to h of m minus n, just replacing h of n with h of m minus n because we are talking about type 1 and type 2 filters, and that's the condition for type 2 filters of even symmetry. So let's move there. H of z is equal to n is equal to 0 to m h of m minus n. Just replace this h of n with h of m minus n and 0 to power minus n. And now, just making it more simple, I bring k and I say k is equal to m minus n. So this h of m minus 1, m minus n will become h of k. 0 to power minus n will become 0 to power k. 0 to power into 0 to power minus m. And the summation will be, when n is equal to 0, k will be from m to k will be m, and when n is equal to m, k will be equal to 0. So that's the situation, and I can further write this equation as h of z will be equal to, just bringing this 0 to power minus m out because that's independent of that summation. K is equal to m to 0 h of k 0 to power k. Now let's look at this. And compare it with h of z is equal to k is equal to 0 to m h of k z raised to power minus k. So just comparing these two equations, what do you think? What is this thing? जी हमजा बोलिए.
सर माइनस एच ऑफ जी, लेकिन सर इसको फिर हमें वेरिएबल चेंज करना पड़ेगा.
This is not minus h of z, it is h of z inverse.
Yes sir.
Because the limits are reversed and you can see the power is reversed as well. So you can prove it that it is h of z inverse. And now we call this equation as so suppose z naught is some constant. Z naught is the zero of the filter. So we can write h of z naught, that would be equal to z naught raised to power minus m, h of z naught inverse, and that would be equal to 0. So that's my equation A. Now what does this equation is telling me? This equation tells me that h of z naught is equal to 0 and h of z naught inverse will be equal to 0. What does it mean? It means that if I have a 0, if z naught is equal to r exponential j theta is a 0 of h of z, then z naught inverse, that would be equal to r raised to power minus 1 exponential minus j theta will also be a 0 of h of z. Any confusions, please ask. हमजा क्लियर है बेटा?
सर हम यहाँ ये कह रहे हैं कि हमें उसकी रेसिप्रोकल लोकेशन पे भी 0 मिलेगा.
जी आपको ये इक्वेशन बता रही है, because it is saying that h of z naught is equal to, this is 0 because from here we are saying that z naught is a 0. We have supposed z naught is a 0 means any location. Suppose I'm sitting here. I suppose this is z naught. Then this equation is telling me that at its reciprocal location there will be a 0 as well. ये रियल 0 था. अगर मैं कॉम्प्लेक्स 0 की बात करता हूं तो उसकी कॉम्प्लेक्स रेसिप्रोकल लोकेशन पे 0 होगा. ठीक है? And of course we have complex conjugate pairs होते हैं, तो we will be having these 4 pairs. So what does this all discussion says कि हमारे पास अब क्या situation है that the complex 0 comments based on what we have done. The complex 0 not on the unit circle. Is a part of set of 4 zeros. यानी अगर हम इसको देखें and we have one single imaginary, आप 0 रख नहीं सकते because you have to have this 0 to have your linear constant coefficient difference equation real. So इस पेयर के लिए आपके पास ये पेयर मौजूद होगा. So single complex 0 which is not located on the unit circle, actually this is related to a group of 4 zeros. ये 4 जीरोस मौजूद होंगे। सपोज मेरे पास अगर इधर कोई जीरो है, एक उसका कॉम्प्लेक्स कॉन्जुगेट पेयर होगा और फिर ये उसके रेसिप्रोकल लोकेशन होंगे। सो ऑलवेज एनी जीरो अपीयरिंग in our linear phase FIR filters, any zero appearing as a complex zero will be a part of 4 zeros, group of 4 zeros में से वो आपके पास आ रहा होगा। क्लियर हो गई बात?
Yes, sir.
Number 2, now the complex zero on the unit circle. There is a possibility that the zero can be on the unit circle. So in that case, that is a part of जी। हमजा मुबशिर, कितने जीरोस का होना चाहिए वो?
सर फिर तो एक ही होगा और डिप आ जाएगी उस लोकेशन पे।
अगर मेरे पास यहाँ पे जीरो हो तो एक ही जीरो होगा।
नहीं सर, एक पोल भी होगा हमारे पास ओरिजिन में।
मेरा बेटा जीरो की बात हो रही है सिर्फ, पोल्स मुझे पता है ओरिजिन पे हैं, मैं जीरोस के जो क्रक्स है वो आप शायद नहीं समझ रहे। आई एम जस्ट टॉकिंग अबाउट जीरोस।
यस सर।
सो तो एक जीरो यहाँ पे मौजूद होगा, और ये जीरो किस लिए होता है? ये जीरो इसलिए होता है कि हैव योर लीनियर कांस्टेंट कोएफिशिएंट डिफरेंस इक्वेशन के जो कोएफिशिएंट्स हैं उनको रियल बनाने के लिए। अगर मेरा सिर्फ एक जीरो होगा तो कॉम्प्लेक्स होगा, यानी क्या हो जाएगा, आर एक्सपोनेंशियल जे थीटा वाली टर्म्स आ रही होंगी। सो इट्स अ कॉम्प्लेक्स थिंग। लेकिन अगर दो हैं तो इन दैट केस आर एक्सपोनेंशियल जे थीटा प्लस और माइनस में जाके वो कोसाइन की टर्म्स में आ जाएगा, रियल हो जाएगा। सो आई वांट दिस कॉम्प्लेक्स कॉन्जुगेट पेयर्स, दिस इज कॉल्ड कॉम्प्लेक्स कॉन्जुगेट पेयर। कम ऑन, दिस इज चैप्टर नंबर 2। कॉम्प्लेक्स कॉन्जुगेट पेयर्स हमारे पास होते हैं। अब अगर मेरे पास ये जीरो मौजूद है तो आई मस्ट हैव दिस जीरो। What about the reciprocal locations? So the reciprocal location of this zero, which is at r is equal to 1, that would be at r is equal to 1. ठीक है ना? Z naught at r is equal to exponential j theta. Z naught inverse will be r inverse exponential minus j theta. So if r is equal to 1, then r inverse will be equal to 1. So इसका जो रेसिप्रोकल है वो यही है, वो यहीं पे बैठा रहेगा। इसका जो रेसिप्रोकल है वो यही है, वो यहीं पे बैठा रहेगा। Got it?
यस सर।
ओके, अच्छा जी, आगे चलते हैं। नाउ सेट ऑफ टू जीरोस, रियल जीरो which is not on the unit circle. जी भाई, is a part of set of how many zeros?
2 0 सर।
Set of two zeros. How? Because if we have this zero, which is a real, not on the unit circle, it will be having a reciprocal, the zero will be located at the reciprocal location as well. If we have zero here, there will be zero here on the reciprocal location. ठीक है? So this will be coming as a part of two zeros. Now एक और जीरो मौजूद है जो कि यूनिट सर्कल पे है अगर रियल। So 0 on z is equal to plus minus 1, that is on the unit circle, but on the real axis can appear by itself. Why? Because if you have a 0 at this location, z is equal to plus 1, 1 over this plus 1, that would be this thing. If 0 is located at this location, 1 over minus 1 will be at this location. So the 0 at plus minus 1 will appear by itself. ये कोई ग्रुप नहीं बना रहा होगा। तो 0 की लोकेशंस के बारे में क्लियर हो गई बात?
Yes sir.
Now the case of z is equal to minus 1, that's important. z इज इक्वल टू -1 को देखिए, अगर 0 जो है हम बात कर रहे हैं अगर इधर है. नाउ दिस इज एन इंपॉर्टेंट केस, जरा इसको देख लेते हैं. वी नो दैट h of z0 is equal to what was the equation? Z0 raised to power minus m. Yeah, z raised to power minus m. Z0 raised to power minus m h of Z0 inverse. Now we are saying that Z0 is equal to, the location is Z0 is equal to -1. So क्या हो जाएगा ये h of -1, and that's equal to -1 raised to power minus m and h of 1 over -1. So that would be 1 over -1 करके इसको हम raised to power m कर देते हैं, and that is h raised to power minus n कर देते हैं, and that is equal to -1 raised to power m h of -1 and h of -1. Okay, so that's my equation. ये observation मुझे क्या बता रही है? Okay, if m is even, ठीक है, m अगर even है तो h of -1 is equal to h of -1, no problems, because -1 raised to power 2 will be 1 and everything will be fine. But if m is odd, there must be some restriction on h of -1. What's that?
Sir,
If
0.
G, in that case, h of -1 वो हो जाता है minus h of -1, and this indicates that h of -1 must be equal to 0. Okay, so what is m? M is associated with number of taps. So when m is even, number of taps क्या होते हैं? Number of taps are m plus 1. So when it is even, it means odd number of taps की बात हो रही है. So it means we are talking about n even की बात हो रही है, even n की बात हो रही है. So इसका मतलब ये है, हमारे पास टाइप 1 और टाइप 2 को हम डिस्कस कर रहे हैं. So इसका मतलब है टाइप 2 फिल्टर्स के अंदर h of -1 must be equal to 0. So again, if we extend our discussion, we have type 1 and type 2 filters, and m even and and odd. In that case, it is type 1. No restriction. On h of -1. So there, if there is any 0, okay, fine, but there is no restriction on h of -1. And here for m is odd, that is n is even, that's type 2. And we have concluded that h of -1 must be equal to 0, which indicates that there must be a 0 at z is equal to -1. Questions, please. The discussion of type 1 and type 2 we had done for 0 locations. So whenever we will be having 0, a single 0, complex 0 not on the unit circle, that would be a part of set of 4 zeros. Whenever we will be having a complex 0 which is on the unit circle, that's a part of set of 2 zeros. The real 0 not on the unit circle is a part of set of 2 zeros, and 0 on z is equal to +1 -1 can appear by itself, but there is a restriction on z is equal to -1 for type 2 filters. There must be a 0 at z is equal to -1. Questions?
सर ये लास्ट बात दोबारा रिपीट कर दें.
बेटा कौन सी?
There must be a 0 at Z is equal to -1.
ये इस इक्वेशन से हमने फाइंड आउट किया। ये इक्वेशन ऑलरेडी हमारे पास मौजूद थी। अब हमने कहा कि अगर मेरे पास Z नॉट जो है वो -1 हो तो अल्टीमेटली वी एंडेड अप विद दिस थिंग। अगर तो M इवन है, M इवन का मतलब है नंबर ऑफ टैप्स जो है वो ऑड हैं, टाइप 1 की बात हो रही है। सो ऑड में कोई ऐसा मसला नहीं है। h of -1 will be equal to h of -1 because -1 raised to power some even value that would be 1. But if m is odd, हमारे पास ये सिचुएशन आ जाएगी, h of -1 will be equal to h of -1. So that's only possible when h of -1 equal to 0. Otherwise there is no way on earth कि हम इस इक्वेशन को satisfy कर पाएं. So this is indicating that when our m is odd means our n number of taps are even. So in that case, we must have 0 at h of -1. H of -1 will be equal to 0. That is, there must be a 0 at z is equal to -1. Have I answered your question, beta?
Yes, sir.
Okay, great. So now let's talk about type 3 and type 4 filters. Type 3 and type 4 is different from type 1 in terms of even and odd symmetry. So here beta is equal to pi by 2 and we have odd symmetry. And in terms of h of n, we are writing it minus h of n minus 1 minus n, or we can say it is minus h of m minus n, or we can say it is minus h of 2 alpha minus n. These are all the same things. But as we started our discussion with the expression using m, this expression, and we had used this equation there. So now we will be using a minus sign for odd symmetry. And as a result, we will be getting our h of z that would be equal to negative आ जाएगा यहाँ पे। टाइप 1 और टाइप 2 के केस में हमने फाइंड आउट किया था it was 0 to power minus m h of z minus 1. Now it is negative sign because of this negative sign in the conditions of odd symmetry. So the restrictions जो हमारे पास थी वो exactly similar होंगी, यानी अगर आपके पास कोई complex zero पड़ा हुआ है not on the unit circle, that would be coming from a group of 4 zeros. If a zero is located, a complex zero is located on the unit circle, that would be coming from a group of 2 zeros. A real zero on not on the unit circle will be coming from the group of 2 zeros, as we discussed here. Everything will be same. The only difference will be the case of z is equal to -1 and z is equal to +1 जो है उसको हम देखते हैं इस केस में। यहाँ पे थोड़ा सा वो डिफरेंट है। Okay, let's see that. Suppose if z is equal to +1, तो क्या हो जाएगा ये h of 1 that is equal to minus, मैं इस इक्वेशन में इसको डाल रहा हूं, minus 1 raised to power minus m and h of 1 over 1 that would be 1. So finally I can call it as h of 1 that is equal to minus 1, sorry, it's minus 1 raised to power m h of 1, and that is equal to, in fact, h of 1 is equal to minus h of 1. That's my equation C. So what does this equation tells me?
Sir, h of 1 पे 0.
That this equation is telling me that h of 1 must be equal to 0, because this equation will only be satisfied in the case when h of 1 equal to 0, and there is no restriction on m. There is no restriction on m because minus 1 raised to power positive power, odd powers of m, that would be giving me 1. 1 raised to power even powers of m, So suppose 1 raised to power 2 is equal to 1, 1 raised to power 3 is equal to 1, 1 raised to power 4 is equal to 1. So there is no restriction on m. There is no restriction on number of taps. H of 1 is equal to minus h of 1, and this is making us, forcing us have a 0 at z is equal to 1. So in type 3 and type 4 filters, when we have odd symmetry in number of taps, we will be having a 0 at z is equal to 1, always independent of the number of taps. यानी चाहे वो type 3 हो या type 4 हो, दोनों cases में you will be having a 0 at z is equal to 1. मुबशिर ठीक है बेटा?
यस सर।
सर टाइप
Clear
1
है?
में तो हमारे पास नहीं होगा ना
जी बेटा?
सर, हम लोगों ने भी देखा था कि टाइप 2 में भी हमारे पास h1 इज इक्वल टू 0 आ रहा था और 3 और 4 में भी। सिर्फ टाइप 1 में हमारे पास 0 नहीं आता।
जी जी, टाइप 1 में 0 हो सकता है, रिस्ट्रिक्शन नहीं है. There is no restriction on that. ठीक है? टाइप 2 में h of minus 1 is equal to 0. There must be a 0 at z is equal to minus 1. टाइप 2 की बात हो रही है. Now टाइप 3 की अगर हम बात करें तो there must be 0. टाइप 3 and टाइप 4 में must be a 0 at z is equal to 1. और अब जरा चलते हैं z is equal to minus 1 को देखते हैं. Suppose in case of z is equal to minus 1, so there is a 0. Suppose minus 1 की अगर हम बात करें, the equation can be rephrased like this, that is minus into minus 1 raised to power minus m h of minus 1, and this can be further extended to minus 1 raised to power m h of minus 1, and that h of minus 1 can be written as minus 1. This minus will be going in the power. It is m plus 1 h of minus 1, and so for even m, even m का क्या मतलब है? नंबर ऑफ टैप्स ऑड है, नंबर ऑफ टैप्स ऑड है तो इट इज अ टाइप 3. सो टाइप 3 फिल्टर्स के लिए h of minus 1 जो है that is equal to minus h of minus 1, which is indicating that we must have a 0 at z is equal to minus 1 for type 3 filters. ठीक है जी, यानी टाइप 3 और 4 में एक रिस्ट्रिक्शन है. टाइप 3 और 4 जो हम बना रहे हैं उसमें ये था सपोज टाइप 3 और टाइप 4 की बात हो रही है. टाइप 3 और टाइप 4 में एक रिस्ट्रिक्शन थी कि एक 0 तो लाजमी होगा यहाँ पे z is equal to 1 पे, लेकिन अगर टाइप 3 है तो इन दैट केस देयर विल बी अ 0 एट z is equal to minus 1 as well. So this is type 3. Because there was a restriction on a 0 that it must be having a 0 at type 3, type 4 में z is equal to 1 पे, but for type 3 we must have a 0 at z is equal to minus 1. Now the questions.
सर अभी हमने टाइप 3 के लिए देखा है, अगर टाइप 4 होता तो
टाइप 4 में ये पॉसिबिलिटी हो सकती है. This can be type 4.
सर ये किसी भी सिमेट्री के लिए है, ऑड और इवन दोनों के लिए?
बेटा टाइप 4 ऑड सिमेट्री है, इवन सिमेट्री है?
ऑड से
टाइप 4 ऑड सिमेट्री है. ये मैंने पिछले सिंडिकेट के साथ किए थे तो here are the zeros. Okay, these are the zeros. So let's talk about these zeros. ये type 1, type 2, type 4 की बात पड़ेगी. Okay. So this is type 1. This one is type 1. any complex zero not on the unit circle will be coming from a group of 4 zeros. So this 0, this 0, this 0 and this 0. इस बात को समझ लीजिए कि हमारे पास हमेशा कॉम्प्लेक्स कॉन्जुगेट पेयर्स होते हैं जस्ट टू हैव आवर ट्रांसफर फंक्शन और डिफरेंस इक्वेशन के जो कोएफिशिएंट्स हैं उनको रियल बनाने के लिए. अगर मैं सिर्फ एक जीरो की बात करूंगा, एक अगर जीरो होगा तो इसका जो ट्रांसफर फंक्शन होगा उसके अंदर कॉम्प्लेक्स क्वांटिटीज आएंगी बिकॉज इट्स लोकेटेड एट आर एक्सपोनेंशियल जे थीटा. ठीक है, दिस इज z माइनस आर एक्सपोनेंशियल जे थीटा, कॉम्प्लेक्स है. लेकिन अगर मैं एक जीरो यहाँ पे भी लेके आ जाता हूँ, दिस आई हैव बीन टॉकिंग टू मेनी टाइम्स, सो आर एक्सपोनेंशियल माइनस जे थीटा, नाउ दैट वुड बी z स्क्वायर माइनस 2r cosine theta plus r square, something like that. So अब ये रियल हो गया है. So that's the reason we always keep a complex conjugate pair. We are not intended to have single zero or single pole which is a complex, which is imaginary. ठीक है, so that's why we are always having complex conjugate pair. That is coming from that concept. अब हम कह रहे हैं कि जब भी हमारे पास कोई इस तरह का जीरो होगा, that is coming from the group of 4 zeros because reciprocal locations पे zeros भी मौजूद हैं. So those एक जीरो इसकी reciprocal location पे और एक जीरो इसकी reciprocal location पे. So that's why any complex zero which is not on the unit circle will be coming from a group of 4 zeros. Agreed? हूँ हाँ तो करते जाइए.
Yes sir.
Okay. Now any complex zero which is on the unit circle, that would be coming from a group of 2 zeros because उसका reciprocal जो है वो यही है. 1 का reciprocal अगर r जो है वो 1 है तो 1 over r भी 1 होगा. So that's why that is coming from a group of 2 zeros. देखिए complex conjugate pair मौजूद है in order to have this real coefficients in our difference equation. Any real zero not on the unit circle will be coming from a group of 2 zeros. ये अगर 0.5 पे था तो ये 2 पे रखा हुआ है. ये अगर 0.75 पे था तो ये 1 over 0.75 पे रखा हुआ है. क्लियर हो गई बात? So that was type 1. जब भी आपके पास zeros होंगे तो इस तरह लोकेशन में रखे हुए होंगे, इन लोकेशंस पे होंगे. Now let's talk about type 2 filter. बाकी तमाम उसी तरह से हैं चीजें. अगर आप इसको देखें तो अगर ये इस जीरो को देखें तो that is coming from a group of 4 zeros. अगर इस जीरो को देखें तो इसका पेयर ये रखा हुआ है. अगर इस जीरो को देखें तो ये इसका जीरो रखा हुआ है और अगर इस जीरो को देखें तो इसका पेयर ये रखा हुआ है. There was a restriction on type 2 filter that there must be a zero at z is equal to -1. So there is a zero. From here we can indicate कि ये type 2 filter है. Then C को अगर आप देखें, there was a restriction in type 3 and type 4 filters that there is a zero at z is equal to +1. And all other things are same. This zero is coming from the group of 4 zero. This zero is coming from the group of 4 zero because this zero is not complex zero, not on the unit circle. And again here as well. But in type 3, there was a restriction, one more restriction, that there must be a zero at z is equal to -1. So that's the situation, that how the zeros are located on your z plot. Questions, please. जी जनाब, any questions?
सर हम लोग टाइप 3 के फिल्टर पे कह रहे हैं कि हमारे पास z is equal to -1 पे 0 होना चाहिए. तो हालांकि टाइप,
दोबारा बताइए किस जगह पे? टाइप 3 पे?
सर अभी आपने हमें बताया ना कि टाइप 3 और टाइप 4 में यानी चीजें सब सेम होंगी, मगर एक रिस्ट्रिक्शन होती है टाइप 3 में कि हमारे पास z is equal to -1 पे एक एडिशनल 0 मस्ट होना चाहिए.
हाँ.
तो हालांकि टाइप 4 के अंदर भी तो ऑड सिमेट्री है, तो उसके अंदर हम क्यों नहीं कह रहे कि यहाँ पे z -1 पे 0 हो?
बेटा ये मैथमेटिकली हमने प्रूफ किया है. क्या हो गया यहाँ पे? अगर आप देखें टाइप 3 और टाइप 4 में So we have mathematically proven that we have in type 3 and type 4, we must have a 0 at z is equal to 1 from this equation. But type 3,
Yes, sir.
we have ended up कि type 3 में we must have a 0 at z is equal to -1 as well. कहाँ पे कहाँ है? For even m, ये देखिए, ये जो टर्म है इसको देखिए, for even m, इस इक्वेशन को यहां से देख के बताया ये h of -1 is equal to -1 raised to power m plus 1 h of -1. It's not coming from the air, it's not coming from the vacuum. But this is the equation which is telling us कि जब m even होगा, in that case क्या situation बनेगी? m even है तो ये situation बन जाएगी -1 raised to power some odd value, and -1 raised to power some odd value will be minus. So h of -1 will be equal to minus h of -1, and that would be only satisfied when h of -1 will be equal to 0. So there must be a 0 at z is equal to -1 for type 3 filter, because m is even, because n is odd. So that's the reason we are saying that we must have a 0 at z is equal to -1 for type 3 filters. This is the case. Have I answered your question, beta?
Yes, sir.
Okay, great. So this was chapter number 5. I'm leaving this chapter here, and now I will be moving to chapter number 6, which is about the structures of the filters. And so the designing DSP systems or designing DSP filters and signal processing systems is basically related to these 4 areas. Number 1 is specification, number 2 designing, number 3 realization, and then implementation. जब हम specifications की बात करते हैं तो suppose we are talking about some filters, a low pass filter, high pass filter, band pass filter, band stop filters, and we have to design those. So from where these specifications are coming? Suppose you are working or you are doing a job at some company and your boss comes to you and gives you the specifications of some filter, and suppose you have to use that filter in mobile phone, and he says that that's the cutoff frequency. What is cutoff frequency? Suppose low pass filter अगर हमारे पास है तो low pass filter के context में हमारी cutoff frequency क्या है? ये मेरी cutoff frequency है. लो पास फिल्टर के कंटेक्स्ट में मैं कहता हूँ 0.2 पाई तक मुझे अपने तमाम फ्रीक्वेंसी कंपोनेंट्स जो हैं मुझे पास करने हैं, और 0.3 पाई से आगे तमाम कंपोनेंट्स को मुझे स्टॉप करवाना है और इनको पास नहीं होने देना. सो ideally it should be equal to 0, but generally we call it कि हम थोड़ी सी attenuation जो है मकसद we can bear with it कि some components are being passed, or this is called pass band ripple. This is called stop band attenuation. यानी stop band attenuation मैं चाह रहा हूँ linear scale पे 0.001 होनी चाहिए. So 0 नहीं है और 0.001 है, तो that's my attenuation. ये जो line है, this is indicating ये मेरी stop band की attenuation है, one of the specifications. Pass band में ideally तो मुझे 1 होना चाहिए, but generally this is not the case, because to make it 1 will make it ideal and we cannot do it. So आप कहते हैं कि यार ठीक है, I'm allowing some ripple as well. So it means 1 और 0.9 के दरमियान अगर वो चल रहा है, मेरा pass band चल रहा है, तो that is okay, कोई problem नहीं. So that's my pass band ripple. ये जो फ्लक्चुएशन हो रही है पास बैंड रिपल है, ये मेरी स्टॉप बैंड एटेन्युएशन है. ये जो लाइन है इससे नीचे नीचे मैं चाहता हूं कि मेरा स्टॉप बैंड होना चाहिए. मेरी कट ऑफ फ्रीक्वेंसी जो है वो ये है 0.2 पाई. मेरा स्टॉप बैंड जो है इसके बाद मैं चाह रहा हूं कि मेरा कोई भी फ्रीक्वेंसीज जो है वो 0.001 से ऊपर ना हो. सो दैट्स माय स्टॉप बैंड एटेन्युएशन. रोल ऑफ क्या चीज है? रोल ऑफ ये है 0.2 pi or 0.3 pi के दौरान, because I am not concerned what is happening in this range 0.2 pi to 0.3 pi. This is called my roll off. So these are the specifications, and when we will be designing in chapter number 7, you will be talking about these specifications, because we will be giving you specification and you will be designing the filters. अच्छा, अब designing क्या चीज है? Designing is you can design IAR filters, impulse infinite impulse response filters and you can design FIR filters, जिनके बारे में हम linear phase filters के बारे में हम बात कर रहे थे. So IR filters के context में आप क्या करते हैं? You are interested in HFZ or HFN, ठीक है, या डिफरेंस इक्वेशन. और FIR के कॉन्टेक्स्ट में आप क्या करते हैं? फिल्टर टैप्स की बात हो रही है. HFN, these are the filter taps and this is designing, ठीक है, ये मेरा HFN है. So in FIR filter design you will be having this. In IR filter design you will be having HFZ. So that's your filter design. And finally implementation के कॉन्टेक्स्ट में, इसके रास्ते में डिजाइनिंग और इम्प्लीमेंटेशन के रास्ते में एक चीज आती है and that is structures. We will be talking about structures in this chapter, but what about implementation? Implementation है hardware specific चीज है या application specific चीज है. यानी you can implement my filter using ASIC, application specific integrated circuits. You can implement it using general purpose DSP chips. You can implement it through C or MATLAB code on the PC. You can implement it on the FPGA, field programmable arrays. ठीक है. So these are the areas related to designing DSP systems. Now, when you have obtained your HFZ or you have obtained your HFN, then you have to present an algorithm with which you will be implementing your system on the hardware. So that's something is we are looking in this chapter. Okay. So let's move forward. So these are the methods of realization: direct form 1 structures, direct form 2 structures, cascade structures and parallel structures. और इस चैप्टर में हम देखेंगे कि direct form 1, 2, cascade और parallel हम क्यों यूज करते हैं, what are the advantages of cascade and parallel over direct form 1 and direct form 2, what are the reasons of moving towards these structures. So ये सारी चीजें जो हैं हम देख रहे होंगे and of course we will be doing lot of examples as well. अच्छा जी, now again इसको हम मिटा सकते हैं. Okay जी, so that's my difference equation, linear constant coefficient difference equation y of n minus k is equal to 1 to n ak y of n minus k, and that is equal to k is equal to 0 to n bk x of n minus k. We have seen these in chapter number 2, we have seen this in chapter number 3 and chapter number 5. So that's the moving average portion, that's the autoregressive portion. And if we are interested in getting the system function, what we do, we take the z transform of that. So y of n ka z transform agar main loon, to that would be y of z minus k is equal to 1 to n ak y of z minus k. That's coming from here, the z transform of this portion, and that would be equal to summation from k is equal to 0 to m bk x of z minus k, and we can further extend this. Y of z is 1 minus k is equal to 1 to n ak z minus k, and that's equal to k is equal to 0 to m bk x of z minus k. And now we can bring this x of z out, and then we can write y of z over x of z, which is nothing but h of z, and that's equal to k is equal to 0 to m bk z minus k divided by 1 minus k is equal to 1 to n ak z minus k, which is this thing. So whenever you have done this exercise before, that whenever you are given a difference equation, you can take the z transform of that and then you can get the h of z. And if you are given h of z, then you can take the inverse z transform of that and you can reach to your linear constant coefficient difference equation. Okay. So now what we are doing, suppose we are going to implement the system. So that's the block diagram representation of our transfer function. So this is the simplest transfer function, the second order system, और इसको हम implement करने जा रहे हैं. So let's see how we are doing it. If we have to implement this system, h of z is equal to b naught over 1 minus a1 z inverse minus a2 z minus 2. If I take the inverse z transform of that, that is nothing but y of n is equal to a1 y of n minus 1 plus a2 y of n minus 2 plus b naught x naught. इसको यहाँ तक ले जाने में कोई प्रॉब्लम अगर आपको है तो प्लीज बता दीजिए.
No, sir.
Okay, now we have to obtain this equation. We have to implement this equation. So y of n is my output. Suppose this node is y of n. I have to get this, and x of n is my input. So x of n is being multiplied. This is indicating that x of n is being multiplied with some constant b naught. And then what about y naught? y naught को अगर आप देखें तो सॉरी yn को अगर आप देखें तो y of n minus 1 चाहिए मुझे. y of n से y of n minus 1 कैसे मिलेगा मुझे? If I pass this y of n from some delay element, and you are aware what is delay element from your digital logic design, that it's a register. So at this location, at this node, I am having y of n minus 1, and this is being multiplied with some constant which is a1, and then this is being added to b naught x of n to get this y of n. And again, I also need y of n minus 2, so I will be passing this y of n minus 1 through this delay element. So at this node, I will be having y of n minus 2. That is being multiplied with some constant which is a2, and then added, and we are getting, now we have implemented this equation. So that's the block diagram representation of this difference equation or this transfer function. Agreed? Any confusions, any questions? जी बेटा.
No, sir.
Okay, great. So बहुत गिचमिच मची हुई है इधर. So ओके जी, थोड़ा सा मामले को एक्सटेंड करते हैं और हम कहते हैं कि हम जरा थोड़ा कॉम्प्लिकेटेड चीजों की तरफ जाते हैं. चलिए, अच्छा जी, ये मेरी डिफरेंस इक्वेशन है. y of n is equal to k is equal to 1 to n a k y of n minus k, the autoregressive portion है, और ये मेरा moving average portion है. And now I am interested, generalized है, there can be m terms in my moving average portion, there can be n terms in my autoregressive portion, and now इस generalized difference equation को I am interested in implementing in a block diagram representation. और मैं इसको कहता हूं, इसको सिंप्लीफाई कर देता हूं, मैं कहता हूं जी ये जो मेरा पोर्शन है, दिस पोर्शन, इसको मैं कह देता हूं दिस इज माय v ऑफ n. सो अब क्या सिचुएशन हो गई है? सो y ऑफ n इज इक्वल टू k इज इक्वल टू 1 to n a k y ऑफ n minus k plus v of n. So this is my input, this is my output. ठीक है जी. तो इस बात का क्या मतलब हुआ कि अगर मुझे इसको इंप्लीमेंट करना है इस डिफरेंस इक्वेशन को, तो हाउ कैन आई डू इट? v of n is my input, y of n is my output, and then I need y of n minus 1, y of n minus 2, y of n minus 3. So I can do it because I will be passing y of n through some delay element, and I will be getting y of n minus 1. I will be multiplying it with a1. This is my a1, and I would be adding it to get y of n. So this is the inverse, and then I will be passing it through a delay element to get y of n minus 2, multiply it with y a2, and then I will be adding it to get the second term in this. And similarly, I will be passing it through delay element to get y of n minus capital N, and I will be multiplying it with a raised to power an, and I will be adding it, and finally adding it here, and I will be getting this y of n, a and y of n minus n, adding to all these terms, and I will be getting this y of n. So that's the portion which is implemented here. Now, what about this one? V of n क्या चीज है? V of n is equal to k is equal to 0 to m bk x of n minus k. So अगर मैं इसको expand करूं तो that would be something b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 so on plus bm x of n minus m. और मुझे अगर इस इक्वेशन को इंप्लीमेंट करना हो तो what's that? The input is x of n, the output is v of n, and what I'm doing this time, there is no feedback component in this because I have to get the delayed version of x of n, which is at this side. So x of n pass through the delay element. At this node, I am getting x of n minus 1 being multiplied with b naught and being added to get b naught x of n minus 1. Then again, x of n minus 1 is being passed through some delay element, and I will be getting x of n minus 2, and that would be multiplied with b1 and then added. And similarly, I will be passing this through delay elements, and this is my x of n minus m, and I will be multiplying it with bm, and then again I would be adding to get x of n minus m. So if we look at this, here I am implementing v of n. V of n is acting as the input, y of n is acting as the output. And here x of n is acting as the input and v of n is acting as the output. And if we cascade these two systems, finally I will be getting this form. X of n is the input and v of n is the output, which is this portion. V of n is the input and y of n is the output, which is this portion. So as a result of that, I am getting this block diagram structure for this difference equation, generalized difference equation, and that's called my direct form 1 structures. If we see this, because we have already talked about that the moving average portion is associated with the numerator of the transfer function, and this is associated with zeros of the system. And the denominator of the transfer function is associated with the poles of the system. So the denominators and poles coefficients जो हैं वो यहाँ पे हैं. A1, A2, A0, these are not the poles, and B0, B1, B2, these are not the zeros. Rather, these are the coefficients. और जब आप इनके roots लेते हैं तो वो आपको zeros बना देते हैं. We have discussed in detail in chapter number 3. So that's my direct form 1 structure. And that's transfer function verification है कि किस तरह से आपने कहा कि आप इस चीज को implement कर रहे हैं. That's Vn is equal to k is equal to 0 to m. If we see here, Vn is equal to, this is your Vn. So Vn का अगर हम k is equal to 0 to m bk x of n minus k, इसका transfer function अगर आपने देना है तो v of z transform ले लें. V of z will be equal to k is equal to 0 to m bk z raised to power minus k x of z, and vz or xz will be equal to k is equal to 0 to m bk z minus k. Similarly, y of n was this thing or this thing. So इसमें आपने कहा yz, that would be equal to k is equal to 1 to n ak z minus k y of z plus vz, and if you are interested in yz over vz, that is equal to 1 over 1 minus k is equal to 1 to n akz minus k. Now you are interested in knowing the final transfer function, which is yz over xz, because the actual system was uske andar y of n was the output and x of n was the input. So we are interested in knowing what is the transfer function, which is yz over xz, and yz over xz is equal to yz over vz, this portion, when y of n is the output and v of n is the input. This is the portion, and that is being multiplied, cascaded with v of z over x of z with a system with v of n is the output and x of n is the input, the portion which is implementing these zeros. And as a result of that, finally, this is your transfer function, and you can get your transfer function if you take the z transform of this y z over x of z, you will be getting in this form. So eventually what we are doing, we are giving some function. So suppose we are given any transfer function we are given. What we are doing, we are taking the numerator, the coefficients which is associated with zeros. We take this coefficient polynomial, and then we are cascading it with the polynomial which is associated with the poles. We are implementing the zeros first, we are implementing the poles after that. कैस्केडेड टू सिस्टम्स हैं, एक h1 ऑफ z है जिसका ट्रांसफर फंक्शन है vz ओवर xz, एक h2 ऑफ z है जिसका ट्रांसफर फंक्शन है y of z over v of z, and when we cascade both of these systems we are getting y of z over x of z, and this is called df1 structure. ठीक है, डायरेक्ट फॉर्म 1 स्ट्रक्चर में आप ये काम कर रहे हैं. और दूसरी चीज, अभी तक हम ब्लॉक डायग्राम के बारे में बात कर रहे थे, जहां पे हम डिले एलिमेंट को इस तरह से एक ब्लॉक बनाते हैं और उसमें जी इनवर्स शो करते हैं. और इसी तरह से जब आप एडिशन कर रहे होते हैं तो यू मेक दिस और उसके अंदर आप ऐड कर रहे होते हैं. बट इफ वी यूज द फ्लो ग्राफ टोपोलॉजी, इन दैट केस everything is, if we have to multiply something, you place a arrow sign and उसके ऊपर जो भी constant जैसे आप multiply करा रहे हैं वो आप लगा दें. इसी तरह से फ्लो ग्राफ में अगर आपने डिले एलिमेंट दिखाना है तो that's enough, आप उसके ऊपर z इनवर्स दिखा दें. और whenever you have to add two things, तो आप इस तरह से अगर दिखाएंगे तो that would be the addition, simplified version of the block diagram. So nothing different. So that's the flow graph version of the df1. The same transfer function or the same difference equation which we did before. This time it is represented in a signal flow graph topology, that x of n is coming in z inverse. So here you are getting b1, at this node you are getting b1 x of n minus 1, at this node you are getting b2 x of n minus 2, and here you are getting bm x of n minus 1. You are adding up all these things and you are getting v of n. Similarly, v of n is going inside this structure, and here you are getting y of n minus 1 being multiplied with a1, y of n minus 2 being multiplied with a2, and y of n minus n, capital N, being multiplied with a capital N, and you are adding all these terms to get this again y of n. So here v of n is the input and y of n is the output. That is related to, this portion is related to the denominator. This is the denominator. And that portion is associated with the zeros of the numerator. This is your numerator, and you're cascading both of these systems. So you're cascading both of these systems. H1 of z is v of z over x of z. H2 of z is y of z over v of z. H1 of z is the zeros or the numerator. H2 of z is the polynomial which is indicating the poles. So that's the thing, cascaded both of the systems, and you're saying that this is my direct form 1 structure. Questions, please. जी हमजा, उसामा, शहरोज, मेहरताबा, no questions beta?
No,
Abdul
sir.
Majid. Okay, there is one thing which is important, and that is कि suppose आपके पास ये given है, suppose एक example थी 1 plus z inverse. This is 1 plus z inverse. And 1 minus 2z inverse plus 3z minus 2. अच्छा, एक चीज पहले ट्रांसफर फंक्शन की टर्म्स में देखें. देखिए यहाँ पे आपके पास पॉजिटिव टर्म्स हैं, bk's आर पॉजिटिव एंड दीज आर अपीयरिंग एज पॉजिटिव. यहाँ पे अगर आप देखें बाय डेफिनेशन ऑफ दिस ट्रांसफर फंक्शन, यहाँ पे आपके पास नेगेटिव में है ट्रांसफर फंक्शन में, बट जो कोएफिशिएंट्स हैं a's A0, A1, A2, A3, but here these are appearing as positive. And in fact, थोड़ा सा इस चीज को हम देख लेते हैं. So y of z over x of z is h of z, and this is given. Suppose that's a given transfer function and you have to implement it using direct form 1. इसकी realization जो है करनी है. So अगर आप difference equation को देखें इसकी, that is y of n is equal to x of n plus x of n minus 1 plus 2yn minus 1 minus 3yn minus 2. Are you sure कि आप इसको find out कर सकते हैं? Because what is this? अगर आप इसको देखें denominator को, it is y of n minus 2y of n minus 1 plus 3y of n minus 2, and that's equal to x of n plus x of n minus 1. So I am interested in getting y of n. So ये वाली terms उधर चली जाएंगी. So y of n is equal to x of n plus x of n minus 1 plus 2yn minus 1 minus 3yn minus 2. अगर आप डिफरेंस इक्वेशन के साथ चलेंगे तो आप वही साइन लगाएंगे अपने स्ट्रक्चर के अंदर जो आपको नजर आ रहा है साइन, अगर आप डिफरेंस इक्वेशन से चल रहे हैं. और अगर आप ट्रांसफर फंक्शन से चल रहे हैं, डायरेक्टली ट्रांसफर फंक्शन से अपना स्ट्रक्चर बना रहे हैं, तो जो आपके साइंस हैं वो अपोजिट हो रहे हैं. अगर आपने अपनी डिफरेंस इक्वेशन इस फॉर्म में लिख ली है कि दैट y of n is equal to some feed forward components and some feedback components, in that case जो भी कोएफिशिएंट्स आपके कोएफिशिएंट्स साइंस लगे हुए हैं फीडबैक कंपोनेंट्स के साथ, वो उसी तरह से आ रहे हैं. गॉट द आंसर? क्लियर है बेटा?
सर ये चीज को दोबारा
जी बेटा,
सर ये चीज को दोबारा बता दें कि अगर हम डिफरेंस इक्वेशन से चल रहे हैं तो पॉजिटिव साइन.
बेटा ये अगर इस तरह से हमने लिखा है कि ये देखिए ये ट्रांसफर फंक्शन था, इसमें देखिए ये -2 था तो ये +2 होके आ रहा है, ये +3 था तो ये -3 के आ रहा है. डिनोमिनेटर इज एसोसिएटेड विद द फीडबैक पोर्शन और द पोल्स. तो ये आपके पोल्स या फीडबैक पोर्शन इंप्लीमेंटेड है. ये न्यूमरेटर है ये आपका जीरोस के साथ एसोसिएटेड है. बोथ द कोएफिशिएंट्स आर 1. b0 plus b1 z इनवर्स अगर हम देखें तो b0 is 1 and b1 is 1. तो ये वाला पोर्शन तो जैसे अपीयर हो रहा है उसी तरह से आएगा. लेकिन इस पोर्शन को अगर आप देखें तो जो कोएफिशिएंट्स के साइंस जो है नेगेटिव हैं वो प्लस होके आ रहे हैं, जो प्लस हैं वो नेगेटिव होके आ रहे हैं, इफ यू आर टेकिंग इट फ्रॉम द ट्रांसफर फंक्शन. लेकिन अगर आप डिफरेंस इक्वेशन बनाते हैं और डिफरेंस इक्वेशन को इस फॉर्म में लिख देते हैं कि y of n is equal to some feed forward portions and some feedback portion, इस केस में जो भी साइंस आपके फीडबैक पोर्शंस के साथ नजर आ रहे हैं उनके कोएफिशिएंट्स के साथ वैसे ही अपीयर होंगे. +2 जो है वो +2 अपीयर हो रहा है और माइनस जो है वो माइनस अपीयर हो रहा है. Have I answered your question?
यस सर.
Okay, great. So अभी तक हमने सिंडिकेट सी के साथ भी इतना ही किया है. So I am leaving it here. और अभी आपका क्विज का टाइम है.
सर 2 मिनट ब्रेक दे दें उसके बाद ले लें सर.
आप 2 मिनट की ब्रेक कर लें बिल्कुल.